All right. Okay, I think my audio isn't connected yet. Okay, good afternoon, everyone. Um, yeah, I'm sorry that we have to do this through a video again, but hopefully next week, uh, yeah, we can be more interactive. But I couldn't attend the class today, so I have to put another video for you. Hopefully that doesn't inhibit your learning. So yeah, anyway, let's start. So last time I think we have studied about the model of the systems, right? So you uh, know what's the transfer functions, signal flow graphs, also Mason's gain. Now we are going to continue further by analyzing what the characteristic of the systems are. So the system here is what we have studied before, which is we have the transfer function, say we have like 2 per s plus 1, right? Transfer function connects the input, say um, R S into the output C. So of course, for different transfer function, we have different output, and for different input, we have also different output. So output here, it is connected to the transfer function and the input of the system. And yeah, so the special characteristics of the output response of the system here is called system performance specification. And we have several procedure, which is by testing, by observing the output response of the system to some typical input. So maybe you have already um, knew this. There are some typical inputs that are commonly used, some basic signals, or here we call them also as test signal. And the reason why we use this because of its simplicity, one, and we can get system characteristics by looking at some of the systems inputs and how the input affects the output by also looking at the transfer function. So there are several purposes. So we can measure the system quality by looking at some test signals as the input. Also, we can get the characteristics of the system or system identification. And also, lastly, we can also perform what is called the model induction, which means that if we have a complicated transfer function, let's say we have 1 per s to the power of 5 plus 1, for example, can we get some simpler transfer function with more or less the same characteristics. So that would be also an interesting topic to study. Now, so these are some let's say categorization of the system characteristics. So this could be divided into time response characteristics, which as the name suggests is the characteristics of the system's system response to the changes in time. So if the time changes, how does the how is the system affected by the change of time? And the second one is the frequency response characteristics. Well, as the name suggests again, how the system changes if the frequency of the say the transfer functions or even the input change. And in time response characteristics, we have two responses. The first one is it's called the transient response, and the second one is the steady state response. So transient here means like something that changes. So uh, in the early part of the system's work, the output may change quite drastically, right? So uh, this is related to how the stability of the system is, or how the transfer function of the system is, and so on. So, for example, if you have the input as the step signal, so this is step signal, and we have the transfer function, let's say 1 per s plus 3. What you have here is something like this. So this would be the output of the system represented by this transfer function. So you can see that there are two parts of this. So the first one here is the transient. The second one is the steady state. Uh, well, there is no clear limit, but we can see from the response or from the output that transient is happening in the early part of the system's work, whereas the steady state is happened in the later part of the system. And for this, there are several signals that could be used, which again, they are called the test signals, and they consist of, I think, impulse, step, or ramp. The most common one, I think, is step. Maybe you already knew that. And the goal here is to know, okay, if I have this input, how the output is given the transfer function of certain order. So that would be our main focus. So just to remind, these are three test signals. So the first one here is called the impulse signal, and this is used to obtain the transient response characteristics. We do not really care about the steady state one. If we use the impulse signal as an input, then for step signal here is used to obtain both transient response characteristics and the steady state response characteristics. So both characteristics are used here. And the next text signal here is the single ramp signal, which is used to obtain tracking characteristics. So I think out of these three, this step signal here is the, let's say, the most often used. And I hope you already are familiar with this. So the equation here is they are shown as this. So in the impulse signal, we have only non-zero value at time 0, which is actually the limit of this is infinity. But I think um, practically we use the value 1 here. And the integral of this from infinity to minus infinity is 1. So that would be the impulse signal. And then the second one is the step signal. Here it is used to, again, obtain some characteristics. And the step signal here they have the value 1 if the time is positive, and they have value 0 if time is negative. So what if time is 0? So that's actually considered like a half, but if we run simulation, well, we have to set this start at 0, right? Because once it's like a 0.001, well, the value here has to be 1. Okay, so it starts at 0. And then the third one is the ramp signal here to obtain tracking characteristic. This out of these three probably the least used, but I think it's nice to know that we can get some characteristics from this signal ramp signal. So another test signal or other test signals here is the one that are periodic signals. So they are the periodic ramp, or also called sawtooth. There is also a rectangular signal and also sinusoidal signal. So this is what's called the periodic ramp. So we have like some um, part of the linear or let's say the ramp signal, but we basically chop this every period t0. We chop this again at 2t0, and we chop this again at 3t0, and so on. And then, yeah, at every period here, they start anew. So this is the main characteristic of the periodic test signal, is that they can like they have like several um, same same parts that are repeated over and over again. Then for rectangular signals here, it starts at some value at 0, and then at t0 it restarts at the same value as in the time 0, uh, and then at 2t0 it restarts again, and so on. Same here for sinusoidal. Well, it restarts at t0, and so on. So t0 here is the period of the signal. And these are some equations that represent those signals. So the main part for periodic signal here is we have this. So xt equals to xt plus k t0, where k is from 0 to t, or from 0 to infinity, I should say. And every the multiply of t0, there is like a restart of the signal, and it happens infinitely, and the signal will not go like beyond this sequence. And this is the equation for sawtooth. So if the time is between 0 to t0, so here we have like some ratio here, whereas for the rectangular here we have a constant here, and for the sinusoidal here we have the sinusoidal signal, the sine or cosine, which could represent the changes of the value of the signals over time. So that's the periodic test signals. So let's go back to the transfer function, and we will now look at some maybe basic systems. Perhaps we look at the first order system first. Okay, now we have a certain characteristic that focus on. So we now focus on the transfer function of the first order system, which means the maximum power here is power of 1, or just S, right? If you have the numerator being constant and the denominator here with, let's say, power of 5, then it's a fifth order system. But if the maximum power here is 1, then it's a first order system. If the maximum power is 2, it's a second order system, and so on and so forth. So here the block diagram is like this. We have the constant or the gain constant k, and we have the time constant tau, and we have 1 here. So that's it. It's very simple, right? So the closed loop transfer function here is the C per R equals K per tau S plus 1. Well, you may wonder, why is it called a closed loop transfer function? Well, this is just a transfer function. So yeah, that means that this is the transfer function of the entire system, right? So since the system is often closed loop, so I think if we say like a closed loop transfer function, it means that the transfer function of the entire system, not a transfer function of like some part of the system, like the sensor only or the controller only or something, but we focus on the entire all parts of the system. So again, there are two parameters here, k and tau s plus 1. So what is this? Or maybe what are the value of this? So for example, if you have like a 5 per 2s plus 1, well, here k is 5, and the time constant here tau is 2. If you have the transfer function 6 per 0.5 s plus 1, well, here k is 6 and tau here is 0.5. If we have, say, 5 per 25 s plus 1, maybe plus 5, here it gets a little bit uh, tricky that we have to conform to this, right? So which means that if we have 5 here, we have to change this to 1. How do we change this? Well, of course, we can just divide all of the values here by 5 so that it becomes 1 per 5s plus 1. And then here we know that k is 1 and tau here is 5. Okay. So I hope that's clear, right? So if we have this kind of form, then we have to conform to this form. The purpose here is to make our analysis easier. If we have, say, s per s plus 1, well, this is not the system that we are considering, so we do not really focus on the system, and it's not it's generally not true what's said about this first order system later if it's applied to this. Okay. Now, these are some more analytical approach on the uh, time domain out of the system. So again, please remember that we have here the frequency domain. Well, what is the frequency domain? If we have um, Rs being 1 per s, and this is say 2 per 3s plus 1, well, we have the Cs here would be like a 2 per 3s squared plus s. What does it mean to have this, right? So maybe we can look at the stability as I will explain later, but uh, we do not really know much, or we cannot really imagine if we only focus on this frequency domain. So I think one approach is to change this back into time domain and see what the graph or what the plot looks like, right? So this is the uh, simplest one with the unit impulse input or the set point, where we have r here equals to delta, uh, and if you remember, the Laplace transform of this delta here is 1. So basically we have the input here is just 1, so it's multiplied by whatever we have, as long as it's in the form of k per tau s plus 1. The output here would be the same. It would be k plus per tau s plus 1. So what does it mean to have such output? Well, we can look at the output here. We multiply this by 1 since the input here is 1. And we have like a k per tau per s plus 1 per tau. So if you remember the um, Laplace transform or inverse Laplace transform. If we have like a 1 per s plus 2, well, the inverse Laplace transform here is e to the minus 2t, right? If we have 1 per s plus 5, here it's e to the minus 5t, and so on, right? So this enables us to get this time domain representation, which is k per tau times e to the power of minus 1 per tau, because this is 1 per tau, right? And this is the gain, so the gain does not change. If this is, let's say, 10, well, we have 10 here, right? 10 times e minus 5t. So anyway, we arrive to this equation of the output. So what's next? So next, we kind of imagine how this graph looks, right? How the plot looks. So the plot is actually here. You don't have to imagine, but we can say that it's like going to zero, right? It's a decaying. So since we have the negative power here, because tau is positive. Oh yeah, tau is positive, by the way. So I hope it's clear. Maybe I should put it here. Okay, let me. Okay, so now it's clear that it's positive. Yeah, so since it is positive, well, it will go to zero as the time goes on, right? Which means the e to the minus zero per something here, it will so yeah, t is getting larger and larger, right? So if you have like a tau here being, let's say, a 5, so you have e to the minus let's say 5,000 if the time is yeah if tau is, let's say, 1, at the time t equals 5,000, this would be e to the minus 5,000, uh, and then what does it mean? It means that this is zero, right? So it goes to zero. If the time increases, this will keep increasing, and in the end, we have e to the minus infinity, which means that the steady state or the final value of this is zero. Okay. Yeah. So that's the general shape of this function. If you have the unit impulse. So next, we have the step response. So this is important because again, most of the, or at least for now, if you study the system, the early part of the system is characterized by the step response, and if the impulse here, the Laplace transform is 1, the step here has the Laplace transform 1 per s, right? So I hope that's clear. Again, doing the same by the same logic, if we have 1 per s as the input and we have the system k per tau s plus 1, now we have the output here would be k per tau s square plus s, right? Which means we can perform the partial fraction decomposition to get these two fractions. So 1 per s and 1 per s plus 1 per tau. And then, yeah, of course, we can do this first. We kind of multiply this, and then we arrive to these fractions by looking at these two fractions here and try to decompose them into two separate fractions. And then this would be like a k per s plus k per s plus 1 per tau. So if we have or if we perform the inverse Laplace transform here, assuming that we have the LTI system, well, it would be just k, right, or k ut, right? And this would be k e to the minus 1 per tau times ut, right? Sorry, 1 per minus t per tau, I missed the t, times the unit step itself. But if we kind of get rid of this, or if we specify that it's the time is more than or equal to 0, then we have k plus k e to the minus t per tau, right? And the important one here is what happens if t and tau is the same. So this happens. Okay, seems that we have some mistake here. Let me check. Okay, yeah, sorry. So this one should be minus. Um, so um, yeah, the next question is what happens if we have t equals to tau? So t is the one that keeps changing, right? At time 0, you will have k times e, sorry, times 1 minus e to like 0 here because we have 0 and we have some values and um, uh, yeah, so this is actually 0. So if you have like this very large time, then it would be like k times 1 to e to the minus infinity, which is basically just k. But what happens if t equals tau? So this is what's called the time constant. So if t equals tau, we have k 1 minus e. So we get rid of those. So those are cancelled. It would be like e to the minus 1. And if you know that this is 1 per e, which is like 0.378 if I remember correctly. So perhaps you can check. Okay, let me see. Okay, so this is the 1 per e, right? So if you remember, e is 2.718, if not something, yeah, 2.718. So if you kind of do 1 per e, it is 0.367. If you do like 1 minus 1 per e, so this would be 0.632. Why is this 1 minus 1 per e? Because that's what we have. Okay. So now we go back to this, and we have here, so this would be at time t equals tau, this part here would be 0.6032, and yeah, multiplied by k. That's the value that will be important. Uh, Actually, it's shown here. So the curve will look like this. So these two actually have the same shape. The difference here is that here in the left we have the gain 1. So if the gain is 1, which means actually it means that at the end of time here we have value 1. So the value is actually determined by gain because as I just mentioned before, at time infinity, this value here would be 1. So the n value here is whatever the value here, or whatever k is, times 1, which is basically k, right? So the gain here determine actually uh, the n time or the value of the n time, but the time constant here actually determine the transient characteristics of the system, right? And then if k is not 1, then say k is 10, then at infinite time, the value is 10 actually. So you can kind of see just by looking at the transfer function what the value of the system is at infinite time because it's dictated by k, right? Uh, and then the time constant actually now determine how fast the system works, or whether we have this shape, or perhaps like this shape, or perhaps like this shape. These are determined by the by the time constant, because we determine how fast the e to the minus something here, how fast this term change. And that term is dictated by the time constant, because we have e to the minus t per tau. And here we have 0.6032, and here we have also 0.632 times k, if k is not 1. So yeah, typically that would be what's called um, the settling time and the rise time constant would be derived based on how fast the system works, which is determined by the time constant. So again, if we look at the offset now, we have the error at the unchanged or the steady state condition, ESS. So if we look at this, because we know that, okay, if the k is k, then the value of the system at infinite time is also k. If k is 10, then the value of the system at infinite time is 10. If the k is 100, then the value of the system at infinite time is also 100. And then we can kind of generalize this by looking at the limit. So this is the final value theorem. So the error here, or the value at the infinite time, the value of the infinite time here is actually could be determined by the value of s equals 0 of the Laplace transform. So this would be s times r minus c, where s is 0. So you have r here, the input, which is the step signal, and you have the output, which is the step signal times the transfer function. And if you put if you put like 1 per s out, if you pull them out, so it would be 1 minus k per tau s plus 1. And you have s here, which means you can get rid of this. We plug in the value 0 here, it would be like a 1 minus k. Okay, and that's the error. We call them the steady state error, or this is ESS, which stands for the steady state. So that would be some some characteristics of this. So if there's a question, well, what should we do if we want to get zero error? Well, we just have to set k equals 1. That's it. And the error steady state would be 0. At the end of time, at infinite time, the value of the output here would be the same as the value of the input, which is 10, right? But if the value of the input is not step, then this could be slightly different. Okay. Okay, so the third one here is the ramp response. So we'll just go through this perhaps relatively quickly. And we have the unit ramp input R here is the multiplication between T and UT. Again, at time 0, it is 0, but at time T here, it is T. because t is positive, right? We assume that we have an LTI system, and now we have the r here, or the uh, input, the frequency domain representation is 1 per s square. Okay, because yeah, if you again remember the Laplace transform, this is the Laplace transform of the t times ut. And now here it's a bit more complicated. We have one more term here, k per s squared. So we do the same step. So we multiply this by 1 per s square. So we get k per s square and minus k tau per s plus k tau per s plus 1 per tau. And here the uh, time domain signal here is kt minus k tau to the power of 1 minus e to the power of minus t per tau. So that would be the time domain representation of the ramp response. Well, what happens if t is very high or at infinite time? You have k t minus k tau 1 to the power of 1 minus e. Yeah, this is minus infinity, right? So this would be minus infinity. So this is 0, right? Uh, so we have here, so this is minus infinity, this is 0, yeah, this is k tau. So here the difference is just k t min tau, something like this. So we have some difference here. If the sorry, if yeah, if t is very large, then yeah, we have also infinity. But let's say we do not suppose that this is as infinity. Yeah, say that it's the same probably. T equals to tau, so this would be 1, and we have this value. At time 0, we have this part here is 1 minus e to the minus or to the 0. So this would be k tau, right? 1 minus 0, and this would be kt minus k tau. So this is what happens if we have t or yeah, t equals to tau. It's rather hard to know. Like of course, at infinite time, the value is infinity because it keeps increasing and increasing. But at time 0, you can get that the value here is also 0. So yeah, let's try this one more time. So if this is 0, so this would be k tau. Of course, this is 0. And this would be k times yeah, tau to the power of 0. So this would be yeah, the value of this ct for some given time. All right. Uh, yeah. So in general, there are two cases or two categories. The first one is transient. The second one is steady state, as I mentioned. And for now, I think we consider the unit step as the input signal, just to simplify the problems here. And we have here the some characteristics of the transient response. They are the first one is the time constant, right? Which is the time needed from 0 until the response achieve 63.2% of the steady state one. Why 63.2? Because it's 1 minus 36.7. 36.7 is 1 per E, right? E is 2.718, and we determine the time constant here as the time needed to um, achieve such value, 63.2. It basically represents the how fast the system is. If the time constant is 5, the system could be quite fast, but if the time constant is let's say 1, the system could be slower, and so on. So it actually represents the speed of the system response. So this is for the first order system. There are several specifications, but I think we will continue this next week. Yeah, we stop here, I think, for today. And please make sure that you work on the short exercise found in the my ITS classroom. Yeah, I'm sorry that we couldn't uh, do the class face to face. Actually, next week I also couldn't come to the campus because I have some uh, yeah family event, and then we will try to now do the class maybe more interactively. I think I will set up the Zoom meeting, and then we can look at yeah the problems. Just look again at the maybe the short exercise, the problems there. Also, maybe if you have time, I would like to discuss the assignments and so on. So don't forget to yeah come to the class online next week. I think that next week, 2 weeks from now. I think we will have a midterm exam, but I think yeah, I will make sure about that next week. I will follow that up next week. Okay, so yeah, thank you very much. I think yeah, we will continue about the second order systems, so third order system, and so on. So the main point here is you yeah you understand something about the stability, also about the transient that is it specifications of the system, assuming that the system is stable. Okay, so yeah, thank you. I will see you next time. Bye. All right, so we will continue. Now we are going to discuss a little bit about the root stability criterion, or root Hurwitz stability criterion. So this is, of course, still related to the concept of stability that we have studied before, where in a stable control system, we know that all closed loop poles, they are located at the left half of the S plane. So, for example, if we have the transfer function like 1 per S plus 2, so here S is minus 2, which means that it is located at the left half of the S plane, right? So S would be here, and we can conclude that this is a stable system. And what if we have like a very, let's say, complicated system where we have, for example, not order 1, but let's say order 5 or something. So we have S to the power of 5 plus S to the power of 4 plus dot 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 and so on.
for example, +2, it would be a little bit tricky to obtain the value of s that makes the denominator 0, or it would be hard to obtain the pole of the transfer function. And as you may already notified, uh, when we are working with this linear systems, we have this transfer function in the form of fractions. So we have like s to the m plus s to the m minus 1 and so on until s to the power of 0. And in the denominator, we have s to the power of n plus s to the power of n minus 1 and so on. So we have like polynomials in both numerator and the denominator of the fraction. And we have this, of course, the requirement that m cannot be more than n. So if this is, for example, 3, then this could only be 1, 2, or 3, right? And by looking at the denominator, we are basically looking at the characteristic equation where we have the um, polynomial again, and we are trying to find what s is, right? And it depends on the complexity of the equation, how many order we have, what is the highest power of s, and so on. If it's just one, for example, like this, just s plus 2, it would be easy. Or if you have like a second order, for example, s squared plus 4s plus 3, it would also be relatively easy because you can get like s plus 1 times s plus 3. Um, and you can get like s equals minus 1 and s equals minus 3. That would be doable, but if we have even more than 2, would be quite tricky to obtain. So that's what we are going to do. We are going to implement some method to bypass the factorization of the fraction. So factorization is kind of hard, and we don't want to do hard things. We want things to be easier. And the root reusability here, this method, it gives information whether there are positive roots in the polynomial equation with s without factorization. So without factorizing the um, uh, the polynomial, so that we cannot uh, it's hard to do factorization. So again, we don't want to do factorization, and there is no like a reliable method to do that. So we have to be, for example, we have to do a lot of practice, or we have to be familiar with like some numbers in there, and it would be hard if we are not familiar with the numbers. So for example, again, like s to the power of 5 plus 5, for example, what is s, right? There should be 5s here because it's the order of 5. So what is s, right? Example, that kind of hard to do again. And what we learned previously is that we have to know s directly, or we have to know the exact value of s to obtain the stability of the system. But here, with root Hurwitz stability, we can like bypass that, and by looking at some patterns of the equations here, we can determine whether the system is stable or not. So these are some procedures to obtain the root for its stability. And of course, we still need the characteristic equations of the system, which is the denominator of the system, a 0 to the power of times s to the power of n, and so on. And we suppose that this an is not 0, so that there is zero root. Oh, sorry, there is no zero root that can be removed. Okay, let me um, fix this. Okay, so for example, if we have like a s to the power of 3 plus s to the power of 2 plus s equals 0, we can factorize out factorize s, and we can get like s square plus s plus 1 equals 0, which means that one of the root here will be 0. So if this is non-zero, not a zero value, then there is no zero root that can be removed. So the first, we write the characteristic equation. The second, we ensure that all coefficients are positive. So I think this is important, that if you have like a zero or negative coefficient, that means that there are roots that have positive real part. In this case, the system is unstable. So what I mean is that we can get, for example, like 1s square, say, minus s or minus 2s plus 3, for example, there is a negative coefficient here, and we can actually factorize this into like s minus 3 s plus 1, which means that uh, we get one pole here positive, so here s equals to plus 3, whereas here s equals negative 1. So that's the positive, there is a pole with positive real part. So how do we know this? By looking at this, well, there is a negative coefficient here, which means that one of them will have like a negative sign uh, in the element or in the component, and which implies that the value of s itself is positive. So that's one characterization that we can uh, look at. So if there is a zero or negative coefficient, it means that there are roots that have positive real part, and we can just say that the system is unstable, or we can rule out the stability of the system. So that would be the um, second procedure. Just try to look at the coefficient. Now the third one is we can arrange the polynomial coefficient in rows and in columns as follows. So this actually follows a certain pattern. So we look at the largest coefficient n, largest power n, and we look at the second largest power n minus 1. So we kind of just arrange the coefficients together. So for example, this a0, we put here a1, we put here, and then a2, a3, a4, a5, and so on. And what is this a0, a1? It is the coefficient of the polynomial equation, of course, by uh, saying that or by writing that a0 is the coefficient of the highest order, and a1 is the coefficient of the second highest order, and so on. Okay, so this is the polynomial coefficients, and we try to arrange this. And next, we actually want to find the um, B. Okay, so A is from the uh, polynomial equation, whereas B is not. So for the polynomial equation, B is what we want to calculate. So B is actually the cross multiplication, the difference of cross multiplication between A and between the A0, A3 minus A2, A1. So like similar to how you like write the determinant of the matrix. So it's actually, yeah, for example, here is A1, A2 minus A0, A3. So it's like, this, like this and this, right? And it's this one is positive, this one is negative, and so on. And B2, we now look at the pivot. So we kind of think of this leftmost column here as the pivot, and we can based our multiplication based on this left hand or leftmost column. So B1 we use A1 A2 minus A0 A3, B2 we use like A1 A4 minus A0 A5, B3 we use A1 A6 minus A0 A7, and so on. So then we obtain the B1, B2, B3, B4 until we run out of elements. So if we run out of elements, then we can just say that it is 0. And we use the same pattern to calculate C, D, E, etc. Where for example, if we want to calculate C, then it would be like B1. So B1 like times um, the diagonal B1 A3 minus B2 A1. If we want to calculate C2, would be B1 A5 minus B3 A1. If we want to calculate C3, it is B1 A7 minus B4 A1, and so on. And we do that again until we run out of elements, and we eventually we'll run out of elements. So we eventually will uh, arrive to the case where everything would be 0, and we will have a triangular shape later. So now the next part is after we complete this process until nth row, until we run out of power, or until it's s to the power of 0, until like here, then we look at the uh, number of roots in the first column's coefficient, so the leftmost column's coefficient. So the number of roots with positive real part are the same as the number of sign change of the first column coefficient. So in other words, we want if we want the system to be stable, we actually want the system, or the coefficient of the first column here, we want them to have uh, unchanged sign. So we want them to be positive, all of them, because again, A has to be positive. Like if it's negative, then the system is unstable. So for example, if you have like say that this is s to the power of 5, s to the power of 4, s to the power of 3, s to the power of 1, s to the power of 2, 1, and this is 0. So we want the coefficient here to be, let's say, 1, 2, 3, 1, 5, for example. We don't want any negative, negative 1, for example. We don't want that. We don't also want like any 0 or any non-positive value. So that's if we want the system to be stable, and that would be useful for us to try to design the stable system. Okay, so that would be the procedures to obtain the Rutherford stability. So there are two special cases. So the special case 1 here is if the term of the first column in a given row is 0, but the other terms are not 0, or if there is no other term, this term can be replaced by a very small positive value epsilon. So this means that, okay, we kind of arrange the coefficient already, and yeah, if the term of the first column here is 0, but the other terms are not 0, we can just replace this by a small positive value epsilon, and yeah, if the sign of the coefficient is 0, then there is a pair of imaginary roots. And if the sign of epsilon is different from the below sign, the sign below, then there is a change of sign, or there is one closed loop root with a positive real value. So that's the first special case of this Rutherford criteria. And the second one is if all coefficients in a row are 0, then there are two real roots of the absolute value with different signs. So this is called the imaginary conjugate. Um, they have the absolute, yeah, same absolute value with different sign. And we form a multiple term with the coefficient of the last row being the derivative coefficient of the next row. And for example, for a 2n degree auxiliary polynomial, there are n pairs of equal and opposite roots. So we can see that there are two special cases. Again, the first one is we have 0 here. Um, and we can replace this with small positive value epsilon, and if the sign of the coefficient again is 0, then there is a pair of imaginary roots, and if the sign is different, then there is a change of sign. Second one, if we have all 0 here in the same row, so that we can obtain the auxiliary polynomial where we can then obtain like the poles and zeros of poles typically of this polynomial equation by looking at this derivative of the equation here. Okay, so these are some examples. So let me actually write this. Okay, now we look at some examples here. So the first here is a simple one. So we have polynomial, the characteristic equations with all of this being positive. So again, if at least one coefficient is negative, then the system is unstable. But if all coefficients are positive, it does not necessarily mean that the system is stable. So actually, we can look at this. So the coefficient here, it starts at the power of 4. So we have s to the power of 4, s to the power of 3, s to the power of 2, and we have s to the power of 1, and we have s to the power of 0. So this would be like 1. Again, we arrange 1, 2, like we stop after the first two rows, we stop after the second row. And then we have like a 3 here, we have 4 here, and we have 5 here. So there is nothing here, so we can just write 0 or we can just skip it. And now we want to uh, compute here the value of the coefficient B1 here, or whatever it is related to the s square. So it would be like 2. So it's like we multiply this diagonally. So 2 times 3 minus 4 times 1. And yeah, it's divided by the pivot value here. So would be like so this is like a 6. So this is minus 4. Oh, yeah, this is divided by 2, by the way. 2, and this is 1. So we can now say that okay, the value here is 1, and we can do the same with the second column here. We multiply 2 by 5, and we subtract it with, now we have nothing here, so this is 0. So we have 10 minus 0 divided by coefficient again be 2. So we have like a 10 divided by 2, which is 5, right? Now we complete the third row. How about this? So since this is all 0 here, so if there is nothing here, we assume that this is 0, this is 0. So all of these are 0, 0, 0, minus 0 multiplied or divided by 2. So this is so 0. And then, okay. Then after that, we do the same with the third one. Sorry, the fourth one. We do that for the third time. And what we do is actually we kind of do the same, right? So 1 multiplied by 4 be like 4 minus 2 multiplied by 5, which is 10. So this would be minus 6. And we divide this by 1. So this would be like minus 6 here. So this is minus 6. And yeah, so we know that there is already a change of sign, or in the other word, we know that one of the pole here is having a positive real value. How about the second one? Well, it does not really matter because again, all of this is 0, this is 0, so we kind of multiply all of the coefficients by 0, and we have like the, yeah, 0 also here. So the last one, if we want to compute, then it's minus 6, minus 6 times 5, and that would be a decrease by 0 because we have like a 1 here and it's multiplied by 0, and we have the denominator here being sorry, not 5 but minus 6, minus 6. So as we look at this now, um, yeah, so this would be minus 6 times 5 divided by minus 6, which is 5. So in this case, this is positive, but it does not really matter in terms of stability because we already knew that the system is unstable due to due to a change of the sign here. So there is two changes of the sign, which means that we have the um, two roots that have a positive real value. So that's how we do this, the stability criterion of root orbits. So next example here, we have the, okay, so we have the equation here. It's a little bit simpler, but now we have the special case where there is a 0 here in the it's actually in the first column. So let me fix this. Okay, yeah, we are back. So now we have the equation s to the power of 3 plus 2s squared plus s plus 2. Now we again perform some arrangements of the coefficient so that now we have s to the 3, s to the 2, s to the 1, and s to the 0. And now as to the 3, we have 1. For this, we have 2. For this, we have 1. For this, we have 2. Right? So now what we do next is we um, compute here the value coefficient of S1. And we have actually like 2 minus 2 or 2, which is 0. So here, what we do with 0 is that we assume that if there is, if the um, 0 here is for this, meaning that we have the proper column here with like a non uh, obvious zero here being only the first column. So we have the epsilon. Epsilon here again is the real positive value. And what we do with the real positive value is we say them as still epsilon as a positive value. So which means that if we have like no further change of sign, we say that there will be an imaginary root, so no positive real pole. So imaginary roots means that uh, in the S domain, they are located in this um, imaginary axis. So okay, so we have this epsilon, and what we do with this is we again say that okay, this is like a 2 epsilon, like a minus 0 divided by epsilon, so this would be like 2. So there is no further change. The only change here is that we change like yeah, this 0 only, right? So from 2 to 0, or from 2 to epsilon, and from epsilon to 2, and so on. And yeah, so if there is no further change, we now know that there is two imaginary roots because there is a change, like quote unquote, in the from yeah, in the sense that we change from 2 to 0, and from 0 to 2. Yeah, there is no positive real poles. There are two imaginary roots, and um, yeah, imaginary roots itself is called like marginally stable. So it's like we have uh, in terms of the time response, we may have like a sustained oscillation. So it does not really diverge, or it does not converge. It just has the same amplitude. So it's not like here. It's not also like here, but it's like the same. So that's often related to the imaginary roots. And the exact value of this of the roots here would be plus j and minus j. Well, this is like the real value. We don't need to find that, but yeah, it's just like to show that okay, this is the roots. These are the roots that are corresponding to the coefficients that we have. So that's the second example. So this is the example of the special case one, or the first special case. Now the next example is the example of this one is another special case one. So now we consider the equation in this. So again, we don't need to know the exact value of the poles. We just need to know, well, the equation itself. So we actually um, yeah, we actually try to find the poles here. So this is just to show like, okay, so this is the actual poles, and you don't have to do this, but just in case that you are curious, you can try to factorize it by your own. So for this equation, we have s to the power of 3, and this has a 0 value here in the s to the power of 2. We actually know that this is unstable because we have already 0 and we have negative here, which is a big red flag. Here we have a positive, so we kind of don't know, but here we have a negative, so we kind of know that we already knew at this time that we have uh, say like a limited, we have some poles being positive, uh, the real value. So here the coefficients are like this. So again, we arrange this from s to the power of 3, now to the s to the power of 2 is 0, now s to the power of 1, which is minus 3, s to the power of 0, which is just constant, which is 2, and we now have 0 here, which means that we change this by epsilon, and this is another case of special case 1 where we can perform a diagonal multiplication, so it would be like a 3 epsilon, and then it's like a minus 2 per epsilon, so this would be like a minus 3 minus 2 per epsilon, which implies that since epsilon itself is positive, since this is positive, so the entire thing here is negative, right? Because it has a minus sign, which means that, okay, we know that there will be a sign change here in the first column of the arrangement. And yeah, in terms of stability, I think we stop here, and we know that there is a pole with positive real value. But if we want to continue, of course, we can do further, and we can kind of multiply this minus 3 minus 2 per epsilon. We multiply this by 2, and we divide this directly with this again, so it's 2. So here this is the same as this, right? And we know that there are two sign changes here in the first column of the arrangement, which implies that there are two roots with positive real values. So that would be the third example. So yeah, well, now we have seen some special cases of the examples of the Rutherford's criterion. Okay, now next example. Right, so this is the fourth example of this Rutherford's method, and then we consider this characteristic equation. This is an equation of the fifth order. So we have s to the power of 5 plus 2s to the power of 4 plus 24s to the power of 3, and so on. And as usual, we perform the arrangements of coefficients, and we end up with 1 here, and we have 2 here for the power of 4. For the power of 3, we have 24. For the power of 2, we have 48, and minus 25, and minus 50, and so on. And if we perform this diagonal multiplication, we end up with 0 here, because we have 24 times 2, which is 48, minus 48 times 1, which is also 48. So this is 0. This is 0. And then the second column also, so it would be like a 2 times minus 25, and it's minus 50, and it would be like reduced by also minus 50. So we have like a minus 50 plus 50, which is 0. So the entire row here will be 0, and we cannot progress any further. And what we do is we get what's called the auxiliary polynomial. So we basically arrange this, so it would be like 2s to the power of 4 plus 48 to the power of 2 minus 50. So we kind of um, derive this, so differentiate this with the respect to s. So it would be like 8 times s to the power of 3 plus 96 times s. And in that case, we can rearrange the coefficients so that it becomes this. So the one with the derivative here now occupies the s to the power of 3 s to the power of 3 row, and we can rearrange this 9, 96, 8, and 96 here for the first column and second column respectively. And yeah, terms in row s to the power of 3, they are coefficient of derivatives of PS with respect to S, which are 8 and 96. And we can arrange the coefficient. So S to the power of 5, we have 1 as usual, as before. And what changes here is this third row with the S to the power of 3, which is having like 8 and 96. So we progress as usual, and now we have 8 times 48 minus 96 times 2 divided by 8 would be like 24. And for example, we have 8 times minus 50, and then it's reduced by 0, and then it divided by 8, so it would be like minus 50 again, because it's divided by 8 and it's um, reduced by 0. So in the end, we can get the first entire first column here, the leftmost column, and we now see that there is one value that has that is negative, which means that we can we can conclude that there is one characteristic equation, or sorry, one pole in this characteristic equation which has a positive real value, which implies then that the system is not stable. So that's the second method, the second special case of the Rutherford method. And then yeah, that's we obtain the stability by knowing the coefficient, right? So what if we want the opposite, which means that what if we want to determine what value of coefficient will make the system stable? So that's actually possible, right? So we can see at the fifth example here. So we have this system k per s times s squared plus s plus 1 times s plus 2, and we want to determine what value of k will make the system stable. So this is important because in control we often employ like the controller, PID controller, as you will study later. And PID controller consists of several, as the name suggests, gains, proportional, also the integral and the derivative. So that's the main components of the PID controller. And if you look at the proportional part, well, it's just multiplied by a constant value, which is k. So now we determine the range of gain k that makes the system stable, which means that we first have to obtain the closed loop transfer function of the system. So we now have this closed loop transfer function. Well, how do we obtain that? Of course, we can kind of simplify this. Say that this is A, for example, so it would be like a K per A per K per A times 1, right? So the feedback part here is 1, and it's plus 1. So if you want to simplify this, you can multiply both sides by A. This is by A. So you have like a K per A divided by K per A plus 1 times A. So you have K. So this is K, and this is like a K plus A, right? Which A is this, the entire denominator of the transfer function, the feed-forward transfer function. So now we get the characteristic equation. How do we get this? We of course multiply this 1 by 1, so it would be like s to the power of 3 plus s square plus s times s plus 2 plus k. So we have now s to the power of 4. This would be like a 2s to the power of 3 would be s to the power of 3 plus 2s squared plus s squared plus 2s plus k. Right. Now we arrive to this characteristic equation, and we perform the coefficient arrangement as usual. Now we have 1, 3. Now 3 again, we have 2, we have k, we have 0. And now this is usual step. So 9 minus 2 per 3 be 7 per 3. And here for the second column, we have 3k. So the next term here is 0. So it would be 0. And it's divided by 3, which is k. Now we have k here. For the third part, we have 2. We can multiply this 7 per 3 times 2. Then decrease by or minus 3k, and this is 7 per 3, which means that it's, you have like a 2 minus 3 divided by 7 per 3, which is 9 per 7k. So we have this value. And the last one here is we have 9, 2 minus 7k times k per, yeah, it's minus 0 per 2 minus 9 per 7k. So it would be like that. And we have k here. So what can we say? Well, to for the system to be stable, so we can see that all of the first column coefficients have to be 0. So, sorry, have to be more than 0. So, this case, k has to be positive, of course, and also 2 minus 9 per 7 k also has to be positive, which means that 2 has to be more than 9 per 7 k, and here k, yeah, it has to be less than some value, which is 14 per 9. So k has to be in between 14 per 9 and 0. So if k is 14 per 9, then the system is oscillating with constant amplitude. So this is what I have mentioned before. So something like this. If it's 0, then that will be the output is 0, right? So that's not in our interest. So now, yeah, the main point is we can say that, okay, if the system follows a certain gain, which is in between 0 and 14 per 9, then we can say that the system is stable. Otherwise, the system is not stable, right? Okay, so that's, I think, our yeah, explanation or our study about the Rotherwitz method. So yeah, that would be like the next step after studying the pole and zero. Here we see that we don't really need the exact value of the pole to know whether or not the system is stable, and we can see that yeah, this is very useful to um, tackle or to address the system where the denominator has higher order, more than 2. It's already hard to obtain the pole. Okay, so I think that's it for this um, video, or for this short lecture. And yeah, next week we will have midterm exam. So please look at my iTest classroom. to to get some information about that. The material would be until the first and second order of the system. This will not be included, I think, this root stability method. So then please prepare, and we will see you next week. So yeah, thank you.